ChatGerry, Understanding the Connection Between VMT and TDA, Why Physics and Geometry Tell the Same Biomedical Story. Number 1410, VMT sharp 738, TDA sharp 021, October 29, 2025. Gerald C. EclaireMD Foundation. Category, Methodology. For the past 16 years, I have studied and written more than 1,400 medical research papers, all based on my own data and without institutional support. My work connects mathematics, physics, engineering, and medicine into a unified approach to understanding the human body. Among my research models, two stand out as the most powerful: the Viscoplastic Medicine Theory, VMT, and Topological Data Analysis, TDA. At first glance, these two systems seem different, and may appear completely unrelated. VMT comes from physics, focusing on energy flow and internal stress. TDA comes from geometry, studying how data points form shapes, areas and volumes, and having different patterns in multidimensional space. Yet, when both are applied to the same biomedical dataset conduct, biomedical researches, their results often match remarkably well. From energy to geometry. In VMT, every biological system behaves like an engineering structure under stress. External factors such as glucose, blood pressure, visceral fat, or sleep act as stressors, while strain represents the body's physiological response, such as disease symptoms. The product of stress and strain defines internal energy, which reflects total metabolic load. When energy is high, the body is unstable and overloaded, unhealthy. As energy decreases, the body moves toward recovery and equilibrium, healthy. Over time, the cumulative, viscoplastic energy shows whether health is improving or declining. TDA, in contrast, does not compute energy. It visualizes how data points from multiple stressors connect and cluster in geometric space through principal component analysis. PCA, TDA defines three main directions. PC1, primary systemic change. PC2, secondary balancing mode. PC3, minor fluctuations. A large TDA area or 3D volume, shaped like a large multi-angled polygon, indicates biomedical instability, similar to high VMT energy. When these clusters contract into smaller, tighter shapes, such as a small sphere or tiny ball, they reflect lower energy and a more stable biomedical system. The bridge between the two models. Both models share the same mathematical foundation: eigendecomposition. Eigenvectors define the direction of change. Eigenvalues define the magnitude or intensity of that change. In physics, this is identical to stress-strain behavior. In VMT, I identified strain rate, which quantifies the direction and speed of internal deformation, as the most critical indicator of system dynamics. By direct equivalence, the eigenvalue in TDA plays the same role, measuring the strength of systemic variation along its principal path. A unified perspective. When a patient improves metabolically, both models reveal the same outcome. 1. VMT, lower energy at each period and declining cumulative energy. 2. TDA, smaller, denser clusters, moving toward balance with shorter distances among data points. In short, VMT presents the engineering energy outcome, while TDA shows the geometric spatial outcome. Both describe the same biological reality from two complementary angles. One physical, one mathematical. Health improvement can therefore be viewed as energy stabilization and geometric contraction, where stress, strain, and topology converge under one universal principle. Stability, health, and longevity arise from energy balance, geometric order, and systemic harmony. Disclaimer: I write this article not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.